Hello, my name is Sven Friedemann. I'm working at the University of Cambridge, and today I want to tell you what is interesting about our electronic structure studies on LuRh2Si2. It sounds like a rather exotic combination of elements, but it is actually a member of a very broad family of materials, including the iron pnictide superconductors and heavy fermion materials. Now, if we want to know the properties of a metal, we need to know its crystal structure, and we usually deduce this from X-ray diffraction measurements. The other important bit is the electronic structure, and here quantum oscillation measurements are a very powerful probe. So now we have investigated LuRh2Si2, which has a tetragonal crystal structure. We know its lattice parameters from X-ray diffraction, but there's one missing parameter, namely the position of the silicon atoms within the unit zone. It's the Z position of the silicon atoms. So we've done high-resolution single crystal structure refinement to find the silicon position, and we've performed numerical lattice relaxation calculations to find the minimal energy corresponding silicon position. They both agree very well. And finally, we could use quantum oscillations to prove that this silicon Z position is right. This is possible because the electronic structure, and in particular the Fermi surface, depends very sensitively on the silicon Z position. As a result, we obtain a very precise knowledge about the lattice structure of LuRh2Si2, and we obtained a very precise knowledge about its electronic structure. In particular, we know that it has got these two Fermi surface sheets. So what are the implications? First, we know that the Hall effect shows a very distinct two-band behavior, and having proven that there are two Fermi surface sheets and having measured them will allow for a very detailed description of the Hall effect and all its electronic transport properties. More generally, we have found that the Fermi surface topology depends very sensitively on the silicon Z position, and this is very common to the whole family of materials. For the iron pnictides, it's the iron-arsen-iron angle, which is equivalent to the silicon Z position. And in the iron pnictides, it determines the magnetic and superconducting properties of the material. Finally, LuRh2Si2 is an ideal reference compound to YbRh2Si2. It has got the same structure, same lattice parameters, even the Z position of the silicon atoms is the same. But there's one difference. Ytterbium has one electron less in its 4f shell. And it is this 4f electron missing which determines all the interesting properties of YbRh2Si2. The f electrons form one band very close to the Fermi energy, which hybridizes via the Kondo effect with the conduction electrons and thereby forms a renormalized band. This renormalized band has a much larger Fermi wave vector, constituting a large Fermi surface. LuRh2Si2 has a full 4f shell, lying well below the Fermi energy, and we are left with only the conduction electrons. In that sense, it represents a small Fermi surface reference to YbRh2Si2. We can now take the measurements on LuRh2Si2 and compare them to those done previously on YbRh2Si2. We find very different angular dependencies of the observed quantum oscillations, and therefore we can rule out the small Fermi surface configuration for YbRh2Si2. As a conclusion, our measurements highlight the presence of the large Fermi surface in YbRh2Si2.